The hummingbird, the beak has an instability. It feeds on nectar from flower, and so it has to be long. The hummingbird also eats insects, and that long beak is not suitable for eating insects. So what it does is it controls the lower beak to buckle, and so it will flap extremely quickly and fast. And now the bird has a short beak, much shorter beak, and that's suitable for eating insects. So this is you can make use of instability to get more benefits. And for more engineering applications, again, the deployable structures, we do use instability to achieve that very extreme deformation without breaking while we, induce that instability. And rollable booms on the solar sails is one example. It uses instability to be able to package in small volume.
Welcome to the Omar Aleli podcast, your go-to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Aleli, and today I'm thrilled to be joined by Professor Kawai Kwok, Associate Professor at Purdue University and a leading innovator in aerospace materials and structural engineering. His research connects ultra-thin composite materials, deployable spacecraft structures, and in-space manufacturing, technologies reshaping how we design and build in orbit. Kawai, it's great to have you on the podcast. Thank you for making the time.
Yeah, thank you for having me.
We know that space punishes every assumption. We're talking about extreme temperature swings, space radiation, no repair crew. What are the unique mechanical or thermal realities that make designing materials for orbit and deep space fundamentally different from designing them for aviation or terrestrial use?
Yeah, I think the main challenge is the space environment. And, I'm a mechanical engineer and deal with materials and structural innovations. So we often have to face, where you have, for example, microgravity in space. So that kind of warp your mind a little bit when you think about, what kind of structures you need. So that gravity does not actually impose a lot of loading in space. So that changes how you think about designing structures. So microgravity is actually more benign on the mechanical performance that you need. But there are other challenges associated with microgravity, right? For example, if you have robotics and you do have to increase the low capacity on the robotics. And so all of that, dynamics of the robotics have to be taken into account. And that's very hard to think about on Earth because, we always have gravity. And so that makes it very unique. And the other part is just the thermal vacuum environment, the temperature swings that you talk about, right, that impose quite a bit of challenges to materials. And you have extreme thermal expansion within a structure that is quite possible whether you're facing the sun or not facing the sun, and so that creates sort of shape distortion and sort of kind of thermal stresses that arise from that that aspect that now you have to take into account that you don't normally take into account in an Earth environment. So there are interesting problems, but we can also think about how to leverage that. And some of that microgravity, for example, you can actually try to make use of that for some purposes. So that's I think one of the unique aspect of space exploration that kind of keeps us going, and quite exciting to kind of think about that dimension.
As weird as it sounds, your research is about programming specific behaviors into the material you develop for space use, like flexibility or a predictable response over time, which bring us into advanced composite materials, particularly carbon fiber reinforced polymers. What makes them unique, and can they replace metal or metal alloy for space structures?
Yeah. So a lot of the driving factors in our design or for space applications are really making them very lightweight. And so composites are very sort of natural solution to that. And we know that they perform very well and being very lightweight. The other property of composites is the almost zero thermal expansion of carbon. And now we don't usually think too much about that for Earth applications again, but actually that's quite critical if you think about the thermal expansion that happened in space. And having something that is not going to expand very much, that does not change the dimensional stability of your structure, that is actually quite benefit of using composites. And but the composites that we use may be a little bit different than typical composites we think about. We use very, very thin composites. So yes, I guess there are many different applications to using composites. So there are sort of very high, low bearing applications like the pressure vessels that you mentioned, and so being the lightweight is the main driver. And so there are composites that we think about very thin and flexible. So those are for sort of spacecraft applications. Again, we try to make use of the lightweight properties of composites. And we're thinking about the autonomy of the structure, that it has to operate in space, being able to control their properties to the space environment and how they actually deploy in space. So that there's something that you can control or engineer with composite materials as well.
When you design for time-dependent response or flexibility, are you targeting a behavioral response curve first and back solving the layup, or the other way around?
So yes, the problem that we are facing, let me give you an example, is we have to package a large composite structure inside a launch vehicle, and then it has to deploy in space. So the design problem becomes that, well, it has to go through two different operations. The first one is, how do you package it? And that's just for transportation. Now, the other part of the problem is, how does it deploy and it starts operating, right? So you're really thinking about a problem that has to tackle two problems at once. And so programming the material properties is one solution to that, right? So you can make it pretty compliant or soft when you try to package a very large structure very efficiently. Now you want it to be stiff when it operates in space. So if you can somehow engineer material that has these variable properties, then you can achieve sort of the best of both worlds.
So how close are we to being able to dial in a behavior, say a targeted stiffness or damping, through simulation before fabrication?
A combination of simulations and prototyping. We try to go through a very rapid design, build, test, iteration. So that's typical what we have been doing in the lab. Is we have a concept that based on a certain principle that we know are going to change properties of the materials, and we start building small prototypes with simulations to give us some idea of the range of properties that we can get. And we start building the actual prototype and testing it out in the lab and see if that can demonstrate those benefits in a smaller scale. And then we work out way up to larger structures.
Kawai, the ability to fold structures for launch is paramount, and your work with Thin-Ply composites is key to this. The promise of Thin-Ply composites is radical deformation without catastrophic failure. In practice, what's the threshold between reversible folding and structural fatigue?
Yeah, so the fundamental challenge is really a very little bit contradictory for deployable structures in space. Is you got to be soft and flexible at some amount of the lifetime of the structure, and then you got to be stiff for the operation. And yes, the Thin-Ply composites is one that you can actually achieve in both worlds to some extent, because in this thin-ply composite approach, we rely completely on deforming the material for folding, and so that's different from the conventional way of thinking about mechanisms or using just hinges and screws and those things to build structure. And so it is beneficial in several ways that you don't need separate parts, and you reduce part count, you reduce the risk of deployment, but you also have the trade-off of being quite flexible. So you ask the question is quite critical. What is the threshold? Can how flexible should it be, right? So that there is a limit to the size of the structure that you build, because we are using very thin materials. It is good for folding and packaging. However, when you deploy them in space, very high shape precise structures is very hard for deployable structures or thin-ply deployable structures to work there. And so there are certain limits, because they tend to get less stiff and less shape precise. And so applications such as telescope mirrors and reflector antennas, those found they're challenging to apply in that arena.
So, what kind of applications would thin-ply composites be used on? Is there anything that you're working on or is available in space right now?
I can talk about one example or one project that we've been working on for a couple of years ago. This is a solar sail from NASA Langley. So we have a collaboration with NASA Langley. They're developing they call it ACS3, Advanced Composites Solar Sail System, and it was launched and successfully. And so this is the first solar sail that is a big kite. Think of it as a kite, but now you use the solar radiation pressure to propel the spacecraft around. So it's very low cost way of maneuvering and moving around in space. Now it's a very giant structure. So you think about a kite, and then there are booms, which is a supporting structure for the membrane of the sail. And those booms have to come out from a small satellite. Think about several U's CubeSats, 12 U's, 6 U's of CubeSats. That's typically what it use as a spacecraft, but it deployed to 7 meters of boom length, and so it's completely rolled up inside the spacecraft, and in space it would roll out. So deployable booms are one of the I think most common and very useful applications. You can also see that in solar arrays. So there are solar arrays that deployed by booms in space. So one of the innovation in solar array, deployable solar array, is the ROSA, is one that attached on ISS. So that was deployed by 2 composite rollable booms, and they are made of very thin-ply composites. And the solar array is being rolled out from there.
Okay, let's move on to viscoelasticity. You've described viscoelasticity and the tendency of those composites to remember their folded shape as perhaps the single greatest obstacle for high precision deployable structures. For an application like a large space telescope antenna, where millimeters of error can mean mission failure, how do you design around viscoelastic creep so a reflector or boom returns to spec after long stowage?
Yeah. So that is a tough problem, and it's an ongoing problem as well. Polymer always have some viscoelasticity, and what the industry or the community is using is trying to get a high glass transition temperature polymer, which really how much creep that the polymer will occur. And so one of the solar sail problem, the project that we just mentioned, part of our work was to analyze how much of deformation of the boom will have after you roll it for some amount of time, right? So that typically they're rolled up in in a launch vehicle, and then you probably sit there. It could be a few months or so, right, depending on the mission schedule, launch schedule. And once you deploy it, you would have some sort of non-straight geometry coming from that creep. So we take into account all that time-dependent simulation. So we've built quite a high fidelity simulations, taking into account the polymer creep properties. And we would simulate that through the full life cycle, right? So from the rolling, and then we stored it for, some specific amount of time. It could be a few months or years. And then we allow it to deploy in a simulation. And then now we go and check if the structural geometry stays the same. So this is, one way that we try to at least understand the problem that we are facing and understand how much deformation are we looking at. And sometimes maybe they're actually fine for the mission and they will be okay. And some other time we have to change the design. So very possibly we can do that with, for example, changing the composite layer layup and making use of the elasticity of the fibers more to limit the deformation due to creep. Or the polymer innovation, getting the higher glass transition temperature, that would also limit the creep deformation in those applications.
Does this challenge of viscoelasticity mean we have to accept a certain margin of error in deployment, or do we foresee a future material or technique that could eliminate this memory problem entirely?
Yeah, this is a great question. It's always exercised my mind. Can this, can we get rid of it, altogether? And that would be really nice, right? And so I think there are other ways of thinking about bypassing that problem, which is, instead of folding the structure, which actually is the cause for this creep deformation, is that, well, let's not fold it and instead maybe assembling or manufacturing directly in space. So then we can actually overcome that problem altogether. We are not thinking building a structure and folding the structure monolithically, but just thinking about moving the parts in space and assembling there or manufacturing the parts up there, so that they're not subjected to creep at all. So that's, I think, it's the new thinking in the community as well, and this is quite an exciting area.
Yeah, we're going to have a full segment on in-space manufacturing and assembly. Do you see solutions coming more from new resin chemistries or from architecture geometries that compensate for the material's on drift?
Yeah, I think there has been innovations from the polymer chemistry, and so but there is a fundamental challenge is when we use polymer, they are very temperature dependent, and the primary way we try to get rid of it is to manage temperature. So if we are able to, first of all, warm it up and fold it, so that it becomes very easily compactly folded. Then in space, we'll reheat it, and so that it goes back to its more structurally stiff state. But now the challenge with that is the temperature management. That means extra power you need to bring onto the spacecraft, and weight and power is very valuable on any mission. And also we have to think about the thermal environment the spacecraft is subjected to, right? So sometimes you also have to protect it from getting too warm unexpectedly from sunlight. So I think it might be a combination of using very controllable polymer chemistry with very stiff composites. So sort of a hybrid approach would be more promising than just using a completely viscoelastic or shape memory type polymer for the structure.
Okay, let's move on now to smart materials. In your work on multifunctional composites, you've used CNTs and carbon nanopaper for built-in sensing, heating, and actuation. This suggests a future that is blurring the distinction between the structure and the system itself. When you talk about embedding functionality like electrical, thermal, or sensing, what criteria makes a function worth integrating rather than attaching as a subsystem?
Yeah, I think the multifunctional structures have a lot of benefit in terms of, again, lightweighting. So normally we think of systems, so, sensors are sensors and structure are structures. And then, any actuators are actuators. They're all different, and you have all different devices you can use. And then system, level engineering is how do you put them together. And now do you typically end up with a pretty bulky, final product if you do that sort of approach. And just because I think, part of it is because, we are structural engineer, we don't think too much about other parts typically. And that goes the same way as other engineers. They don't think too much about structure. But then the multifunctional structure thinking is really let's try to remove these boundaries or remove these interfaces. Can we have a structure that has all these properties that, if in the case of, for example, my work where we try to heat up the polymer composites to change its properties, right? So you have to have heaters, but then we want it to be lightweight too. We don't want the heater to carry a lot of weight, and we also want it to be pretty easily fabricated part of the structure, and potentially it adds benefit to the stiffness. It's also great. So kind of we were thinking about what kind of materials can deliver that sort of myriad of properties, being stiff, lightweight, and it's actually conductive, and so we can heat it up. And it's kind of inside a very thin form, so we can still fold it. So sort of all that properties. So going back to the drawing board and kind of looking at what kind of materials are there any materials that can actually deliver that sort of thing. It's kind of the multifunctional thinking behind the design.
How do you prevent overcoupling so a heater failure doesn't also take down your strain sensing or structural margin?
Yeah, this is a great question again. Yeah. So, for example, the carbon nanotube papers that we use, you can actually use it as a sensor and a heater at the same time because it changes conductivity as you stretch it. So it gives you a signal. And so there is sort of a multi-physics phenomena that goes on in the CNT material and also the microstructure of it. So there are several levels of engineering that can happen to sort of make those properties work together, right? So we can engineer the microstructure of the CNT so that changes sensitivity of the strain sensing. And then the overall conductivity determines the heating performance. So there are actually independent factors. Obviously, they are coupled, but they're not extremely tightly coupled. Technically speaking, we're talking about the conductivity, and the other is we call it piezoresistivity. That is, only the change in the conductivity when you have a strain applied. And so there are these regions where you can work out, you can have high conductivity, also low piezoresistivity, or vice versa. And so that allows you to put that in your design of the structure.
Kawai, rockets and their fairings still dictate geometry. Anything larger must fold, roll, or inflate. Payload, I mean. We have so far discussed bendability, memory, and multifunctionality of materials, smart materials. How do you define a deployable structure in engineering terms, let's say? What separates it from mechanisms that simply extend or unfold?
Yeah, so we call deployable structures, my definition, or the way I think about it, is really the design intent. So there are many structures that change shape and geometry and size. And one example is morphing aircraft. They change in geometry. But their design purpose is very different from deployable structures. The main difference is that deployable structures, we are really aiming for the size reduction. And so we are talking really extreme change in the size or dimensions. And geometry wise, it is not so much that we try to control the geometry while it is operating. So that's different from, for example, morphing aircraft. If I make that contrast, that might help. Morphing aircraft, you would like to change the airfoil shape as it's flying to optimize performance. So you're continuously making that change during operation. But deployable, I'm thinking more about kind of size expansion, and we don't change them during operation. So this is kind of solving a sort of a different problem would be how I look at it. Mechanisms are, I think, is a type of deployable structures. We also think about it as deployable structures. But then the approach that we use is in composites is typically making, in Thin-Ply composite is using deformation of the material instead of discrete movements of joints.
Among future missions like solar arrays, antennas, habitats, which application best demonstrates deployables moving from experimental to operational maturity, and what unlocked that shift, if any?
Yeah, I think that the power. I think solar array is a big area that we would see more of. Larger structures that are needed, then we got to provide that large structure, and deployable structures is, I think, one of the main ways of doing that. And because I think one of the reason is because also that the shape requirement on a solar array is not very tight. And so they're different than reflector antennas or optics telescope.
You cited inspiration from Ladybug's wing deployment, a biological solution to compact stowage. Can you share the Ladybug story?
Yeah, yeah. So this is really one of the ideas that happened to us by chance. So we had I've been working on deployable space structures and not so much on aircraft or drones, but a chance conversation with someone at the Navy department. Really thinking about drones that can be launched from small compartments, and they have to be deploying very quickly in air and start operating as an aircraft. So at first I thought it was difficult for me because we deal with the aircraft environment is very different from space. The loading is quite difficult, so it challenges the deployable structure design. But then I came across this paper, which is written by a friend from Japan. So we met when I was a student, grad student, and he was a visitor and doing work on origami type of structures. Then the long story short is, he studied ladybugs that actually fold their wings and they flip out very quickly and then they start flying. Right? So that's a great inspiration for us. So we kind of study their papers and understanding that actually there's a regime where you can make that flexible, thin, deployable approach work, even for aircraft. So there's a size scale to it. And so that actually gave us the starting point for how we design our deployable airfoils for drones.
So when translating a biological or origami motif, how do you decide which principle to preserve, like a curved creased kinematics and such, and which complexities to strip away?
So we always get some inspiration from the bio world. I think the difficult part is to extract the essential principles that can be translated to the application that we're looking at. And for example, we're looking at ladybugs, so it's going to be pretty difficult to think about that same approach working on a very heavy lift aircraft. At least not now. That we don't think that is possible for now. But there are problems that share similar characteristics as the insect flight, meaning that smaller ones, lower speed type of applications. Then there is a regime that can be applicable. And often we have to make modifications because the insect wing is very tailored to the insect. And we are not building an insect drone. And so we have to size up and scale up. And along the way, we also bring in some conventional design elements that we know work well for drones. And so that is sort of a fusion process happening between bringing in new elements to some conventional type of drone design.
So, how has studying natural deployables changed how you teach or think about structural efficiency or failure in aerospace design?
Yeah, I think this is quite. I mean, it always amazes me that there are, how deployable structures are actually very common in nature, in biology. And it's not how I brought up or train in school when we think about structures being static. So I try always now to bring in some more of that elements in just teaching that there are the problem that we are facing, right? So what are the actual requirements on that, and we can think about structures that are being quite flexible and still they can do the job, right? So even though they intuitively could look pretty flimsy, and so it really getting down to working out the equations that help you have a good standing point whether that is feasible. So that kind of changes my mind quite a bit. You're just thinking about this small insects.
Are there other examples from nature or even ancient arts like origami that you believe hold untapped potential for solving modern aerospace engineering problems?
Yeah, we think a lot about birds now, and that has been a lot of other researchers in the aircraft domain have been looking at birds for very deeply, and we're trying to get inspiration on that also to kind of enrich the properties of our foldable wings, and thinking about their feathers, so they have some amount of morphing capabilities, so they're not just foldable but they also morph. So there's kind of two different characteristics in one structure. So we try to emulate some of that too, so that we don't have only a deployable drone, but that drone is also sort of morphing, optimized that to a certain extent. So we've been studying feathers, mostly collaborator aerodynamicist. He studies the feathers and how we can again translate some of the principles to an actual airfoil, which has no feathers, right? But we try to translate that underlying principle and replicate the same type of behavior without using feathers, but some other means of manufacturing.
Okay, now let's move into engineered instability. Kawai, you treat buckling as a feature, designing bistable shells that snap to deploy fast and light. What convinced you that engineered instability could be engineered safely, not a lab trick that should be avoided?
So I think we a lot of instability. We thought of it as a failure mode. That's how we look at it. But I now think about failure is very specific to application, and it's a failure for a certain problem, right? Obviously, instability in structures is drastic failure for aircraft wings. So if you have buckling of the wing, then that's or the rocket. If you buckle, then that goes away. The structural stiffness go away. But that is for a very specific, a failure mode for that specific application. But now, if you like some very dramatic deformation, if there are applications that require that, then the instability becomes a friend. And so that kind of turn around instead of avoiding it, you really actually try to use it.
This could be challenging for our audience to understand. How can instability be a good thing? Can you give an example?
Yeah. For example, so again, let me take an example of from nature, the hummingbird. And so the hummingbird, they have a beak, and now the beak has an instability. So typically, it feeds on sugar or nectar from flower, and so it has to be long. But it also eats insects. So the hummingbird also eats insects, and that long beak is not suitable for eating insects. So what it does is it controls the lower beak buckle. And so it would flap extremely quickly and fast. And now the bird has a short beak, much shorter beak. And that's, suitable for eating insects. So if you think about birds, the birds with short beaks, they eat insects. They don't feed on nectar, right? So the one that with long beaks, they feed on nectar, right? But now hummingbird, because he can do both, it actually eats both insects and nectar. So this is, you can make use of instability to get more benefits. That's the case of hummingbird. And for more engineering applications, again, the deployable structures, we do use instability to achieve that very extreme deformation without breaking. Obviously, that is, that there's a requirement that we don't break while we, induce that instability. And rollable booms on the solar sails is one example. It uses instability to be able to package in small volume.
Are there limits like material scaling laws or control issues where using instability still feels too risky for flight certification?
Yeah, there are certain stiffness that limitation when it get deployed. So one of the enabling characteristics for stability or buckling is the thickness. So that's why we use very thin materials and structures. If they are thin, you can induce instability, creates a lot of deformation or geometric change. But now it remains thin all the time. So when you want it to take load, it still remain a pretty thin structure. So there are some limits to how you employ that strategy. The other, challenge to that is if you have a structure that is open section instead of closed section, it's easier to buckle. So a closed circle is a closed section that's very difficult to buckle it without breaking. But if you cut a slit onto it, it suddenly become open section. Is actually very easy to buckle without breaking. So there are some ways to engineer that. Now you lose some of the stiffness because of the open section. And so we have to be careful with the stiffness requirements and also the folding requirements.
Okay, let's go back to something you mentioned about the propeller blades for drones. Your work on deployable propeller blades, which could be launched from a canister, as we discussed, is a fantastic real-world application for harnessing instability. It extends these ideas into dynamic rotating systems. What unique aerostructural problems emerge once the deployable elements must spin?
Yeah, so the one of the problem that we're actually actively working on right now is what is the dynamic deployment process look like for a structure like this. So the structure, after being folded, it really relies on the elastic string energy in the structure to deploy. Aircraft is already launched, so it has a certain amount of forward speed in air. So any sort of deployment will be resisted by sort of the airflow. And so how do you actually make sure that deployment can happen reliably? Right. So, and then the launch condition can be different, right? The speed can be different. They can be variable. You can have gusts that you cannot predict. And that is something that we have to take into account, as it's quite challenging for us. So we have to reproduce that sort of variations in wind conditions in the lab to investigate that problem. And we're actually building a launcher, and so that we can reproduce that sort of environment and do dynamic deployment testing, making sure that it can do that deployment as expected. The other part is the stability of the aircraft. So this is more, thinking about the whole system. It's not just the deployable structure, but obviously the structure, when it deploys, it changes the shape and the forces and the inertia of the structure now. And how do we keep stability of the aircraft during that process? So it's pretty drastic change in geometry. And so that is a challenging problem for us. We're still trying to look at it and understand the challenges in that process.
This has a clear defense application. But what are some of the less obvious commercial or scientific applications that a technology like this could unlock?
So one of the potential applications would be a rescue drone. So the characteristics or differentiator for that deployable airfoil or deployable propeller blades is that you encounter, or you very often encounter congested environment that is without a large open area for you to take off, and so a launcher is easier for this to get airborne and keep operating. So you can overcome that limitation. So environment, so applications such as rescued, we're envisioning that this might be able to adapt to different launch environments. And the other application is, or the other benefit is, if we can allow it to fly longer by making the propellers and the airfoils longer, efficiency tends to go up with those. And so you can think about just having higher performance aircraft, higher payload, longer endurance aircraft, but still launchable. So drones that can fly longer, but no, without the limitations of a storage area and a large runway.
Looking ahead, could deployable rotors redefine what reusable means for planetary or atmospheric exploration vehicles?
I think most of the structures in space exploration have some type of deployable elements, and so it's going to be a combination of mechanisms, deployable elements, and I think assembling autonomously in space. So I think deployable structures have a role to play, but I think it's going to be an all-out, very hybrid approach again. Again, looking at the exploration that require robots, for example, but you also require solar arrays, solar arrays to gather energy, and you need reflector antennas to communicate, right? So those are typical, applications where you can, you want to make use of deployable structures.
So deployable structures have been revolutionary, but your latest work is focused on the next paradigm, in-space manufacturing and assembly, or ISAM. This is a shift from launching folded structures to launching raw material and robotic factories. What fundamental shift in mindset or engineering philosophy does ISAM demand from designing for launch to designing for assembly in orbit?
Yeah, I think that the biggest driver, the biggest difference is we come from thinking a lot about the structure to thinking about the manufacturing process. So we've always been thinking about, in the deployable structures approach, better deployment mechanisms, more efficient packaging schemes, thinner materials, right? So these are the usual ways to increase the size of the structure. However, it has a certain limitations still with all those improvements. But with in-space manufacturing and assembly, we are actually thinking about, what you can launch is not the structure, but you launch all the things that you need to assemble in space. So the requirement now becomes, I think less on thinking about structure, but what are the parts that you want to send? Or what is the material feedstock that you want to send? And they are actually ready or easy to be manufactured autonomously by robots. And also the processing equipment that and the tooling that enable that manufacturing process. So all of that, we're typically right now think about manufacturing, they are all happening on Earth, right? So all these tooling and equipment, the feedstock, all of that, we don't have to think about them as, very lean and lightweight. But now we have to think about, can we minimize tooling? Can the manufacturing process be more flexible that you don't have to create a lot of molds or tooling for that? Energy, can we reduce the amount of energy that you use for these processes? Thinking about the limitation again of space, very limited in power. The logistics of launching those is difficult, right? So mass and volume, again, so still kind of same constraints, but shifting to the manufacturing equipment and materials.
So, do you see this transition happening first with government missions or commercial ventures? And what will it take for the transition to become economically irreversible?
Yeah, I think that at the beginning, the government will be the big driver to demonstrate these technologies are actually feasible and the capability that we can deliver. So I think that there are, some cases that you can think about. Again, the solar power is, I think, one big and good example, and maybe a valuable potential business case for that is if you're able to build that energy and beam that back to Earth, then suddenly it has a lot more immediate benefits you can see, right? Providing energy, renewable type of energy to Earth with high efficiency. And that gives a lot of, I think it would then accelerate the economy on pushing more in space manufacturing capabilities to building larger structures. And obviously the government NASA has plans for going to the Mars, right? So that's, building that infrastructure in space for exploration. But that probably will be mainly, borne by the government, not the commercial sector.
Kawai, a key enabler for ISAM is your work on welding thermoplastic composites using embedded carbon nanotubes, essentially making the structure's joints their own heating elements. This is an incredible, elegant solution, by the way. How do you arrive at this specific idea? And what specific properties make thermoplastics and nanocomposites suited for robotic welding and a more viable path forward than other joining methods like mechanical fasteners or adhesives for a robotic in-space environment?
Yeah, so thermoplastics have some very interesting characteristics. One of the main reason we pick it is because it only requires thermal and temperature and pressure treatments to make the composites, to join the composites. No special parts to be made. For example, mechanical fastening, you typically need some inserts to be embedded in the composite structures, and you have screws that are metallic parts alloys to make those fastening joints. And with this joining method of welding composites, you reduce the complexity of those parts. You less number of parts, less number of different materials, and you can join them without sort of chemistry. It is really just heating and clamping them together, and it's reversible. So you can actually take it apart by de-welding it or debonding it. And so that, again, is something that is different from the aerospace composites right now, which are mostly thermoset. You can't really, rebond it without a lot of, surface modification and so on. And so the thermoplastic composites have these very sort of flexible characteristics that make manufacturing them flexible in space. And we have to think about also they're going to be done by robots. So the easier the manufacturing process or the welding process is, the higher chance that it will succeed. Reducing part counts, reducing complexity of the parts, reducing the number of steps that require for the process.
Are we closer to qualifying such joints for mission critical structures, or are there still unknowns in long-term durability and radiation response? What are the biggest challenges to making this vision a reality?
Yeah, I think there are still unknowns. So thermoplastic composites, I think they've been demonstrated in the aircraft industry very rapidly in the recent years. And there's also a lot of efforts in using them for space applications. And right now, I think there are requirements of doing that in space. We're heating material up to a pretty high temperature. So there's heat that needs to be dissipated after the welding process. This is one of the main driver or the problem that we have to tackle that is different from welding on Earth. So how do you get rid of those heat? If they go to other parts of the spacecraft, that is going to be a big problem. I think this is still in development, demonstrating the technology on maybe secondary structures that would be easier to demonstrate. and moving up to primary structures.
Yeah, one of your most intriguing ideas is reversibility, structures that can be disassembled and re-welded. How does design change when unbuilding or reversibility change the entire life cycle logic of a space structure and is on the roadmap from day one?
If we have so right now, all the composites are not most of the space applications composites are thermoset, and so it's hard to think about reusing or recycling some of those current composite in space to be weldable and joinable. So moving to thermoplastics kind of changed also the design paradigm. So you can think about now that the structure is not going to be used in a single mission. It can be reused. We can think about it, having a first mission. Once it's completed its life cycle, we can repurpose the structure for a different mission. So we have actually a project with NASA last year, just thinking about that. Right. So yeah, so that we are thinking about that if you have a lunar lander that goes onto the aircraft, on the lunar surface, that lunar lander has a lot of structural value. It's a very robust structure, but it has achieved its purpose as a lander. But its elements are extremely valuable as a structure. So if we are able to take it apart, we configure it into a solar tower, right? That we can place on the moon surface, hang a solar array that becomes a permanent structure, infrastructure there. Then that would be a great reuse material, reducing the amount of total materials we have to send, and just making the whole process a bit more sustainable. And so, yeah, we've been thinking about that, with thermoplastics that really can achieve that. So going forward, that would, think the structures that go into the design process, I think thermoplastics is going to be in a lot of people's mind.
So, have you tested thermoplastics in this case so far, or it hasn't been tested yet?
Yeah, some of there are thermoplastics. The thing that I think everybody is mostly interested in is a polymer called Beak, and so that's a high performance engineering polymer, chemically stable, so quite useful for space applications. Has been tested for under space environment as well. So now the question is how to manufacture them, join them, and process them. Which is a different problem because we kind of change the material and also applying different treatments to it. Yeah, so that's where I think a lot of people are looking into and having interest in.
Okay, so just to be clear, these materials are like we have to carry them from Earth, right? We cannot process them in space or like in situ resource utilization.
Yes, this is something that we'll have to bring from the Earth. It's not something we harvest on in space.
Kawai, you recently led a NASA-funded effort around this concept, like we discussed. What were the hardest technical or cultural hurdles in convincing stakeholders that unbuilding could be as valuable as building?
I think having demonstrations are critical. So we've done some prior work before we started on this project. So understanding the kind of fundamental characteristics do help convince other people about the feasibility. And really, I think that also there is some really characteristics of the aerospace thermoset composites that we know cannot possibly deliver the type of characteristics we want. And so I think there's a combination of seeing the limitation of what we currently can do and kind of contrast that with this type of material that can actually close the gap. I think making that story is useful. It's difficult to get that across sometimes. But yeah, that has been the way that we try to think about this, definitely to get people to on board.
So, what would a skeptic misunderstand about your work or vision?
Yeah, so there are some technical limit barriers to this that often make people skeptical. One is energy requirement. So energy to process this thermoplastic is quite high if we want to get the type of mechanical properties. And so typically you go to about 350 degrees Celsius to process peak. You can even go higher to get better mechanical properties. So that is the power you need to achieve that is going to be more than acquiring doing thermoset composites, and so that's one often very one of the question that people would ask: what is the energy to do that? Can you actually deliver that in space in a larger scale? The other part is, what is the tooling or the heating requirement, the tooling and accessory that you need to bring with you. So this is, again, robotically assembled. We envision it to be. So how can you then actually do that heating and all of that with and assembling autonomously? And how does the robot look like? Where they get their power. How do they move along the structure? And the structure is huge, and we think about the robot to be actually smaller than the structure, right? Quite a bit smaller. And so that's, again, the skeptic, not the skeptic, but a challenge that we always see is now the building equipment is going to be smaller than the material or the structure, right? So how do you actually create that or move that manufacturing equipment along different parts of the structure? So so there are some of these challenges that we need to solve.
When you think about robotic assembly in orbit, where do you see the bottleneck? Is it precision sensing, path planning, or the physical interaction between robots and the deformable material?
Yeah, I think about um, the power, the volume, and the mass of the robot. So because a lot of the robots that we can gather on Earth and manufacturing robots, they are fairly bulky and large, and they're fairly static. So they don't move around. Typically, you have a robotic arm and it's stationary, and then what is being moved around is the part. And now we try to revert that thinking, because the structure is going to be built that we're going to assemble is going to be large, and we want something that is lightweight and small that we can fit inside the launch vehicle, right? So again, the manufacturing equipment shouldn't be too large, and its scale and it shouldn't scale with the structure we want to build, right? So if the one day that we decide to build a larger structure, 10 meters, the robot shouldn't also need to be bigger, right? So we want to decouple that sort of scale dependency. And so thinking about that, really changed quite a bit of how you think about the robot, right? So they got to be a little bit more agile. They got to be mobile. Maybe they need to move along the structure. And so that is something that I'm trying to get a few more collaborators to work on. I have colleagues from robotics background, that becomes quite a challenging problem for them too. That kind of shifting away from large, heavy, bulky robots to something a lot more mobile and lightweight.
But if you were given, let's say, access to the International Space Station, whether inside or on the outside, to do an experiment, what would your first experiment be?
Yeah, so we try to really simulate space environment as much as possible in this lab, and that means thermal vacuum environments. So a very large thermal vacuum type facility would be ideal for us, especially thinking about the thermal process that we're going to put into the material. So that is very critical to this sort of research. And another part is microgravity, and that is hard to simulate on Earth, and especially for larger systems, or if you want to demonstrate robotic operations all under microgravity. So that is a tough equipment. So we can we're building type of gravity compensation system for robots. So we can actually sort of hanging a robot, but it is sort of freely moving and do its operations that we intend to do, but then compensate or minimize the effects of gravity. So that gives a lot of insights for us to understand how the actual robot would operate. So there are some non-intuitive phenomena that we don't expect when we have gravity. The robots are always stable, is sitting on the ground, and right, but we don't have that in a space environment.
Kawai, you've laid out a clear technological path from advanced materials to deployable structures to robotic assembly. If we project this trajectory forward 20 or 30 years, what does a bustling cislunar infrastructure built using these principles actually look like? What kind of structures will we see that would be unrecognizable to us today?
Yeah, that's a big question. Cislunar infrastructure. Yeah, definitely. Coming from a background, I'm a structural guide, and having the power infrastructure is going to be very critical to a lot of things that we do. And doing that sort of permanent power station in the cislunar environment, that would be one thing that we keep thinking about. What kind of energy actually can allow us to expand the operations. But then, thinking about energy, then there is the problem of dissipating the heat coming from that high intensity of energy. So the infrastructure got to be followed in terms also not from just the power harvesting, but how do you actually do this sort of heating, cooling, and control and management. So there are definitely other infrastructure that is needed. We have maybe depots on the orbit that allow us to spacecraft to go back and forth and refueling along the way through that long distance. This is infrastructure that I think the power to me is quite critical to enable all of that.
What unsolved problem or new direction most excites you right now? The challenge you'd want to tackle in the next decades?
Yeah, I think that thinking about the full cycle of manufacturing and reusing and recycling material in space, I think that is challenging. It's something that we haven't have the bandwidth to think about, but it's quite exciting. Just thinking about what kind of materials once you send into space extend or use as much as possible, maximize its use in space, and either through reconfiguration, reassembly, or completely just breaking down the material for rebuilding in a completely different device from out of that. And so that, over time that the manufacturing becomes less and less dependent on sending things from the Earth. And more just, becoming a little bit more self-sustaining sort of life cycle completely in space. And so I think that manufacturing is just the first step, and there are thinking about the logistics and how do we get independent from Earth as much as possible. So what kind of technologies, the in space, in-situ resource utilization that you mentioned about, I think that's critical, right? So we can, as much use on-site materials. I think material science has a big part to play. How can we get hybrid properties from this kind of in-space material and on-Earth material? And so that's one of the big question to tackle.
If you could leave our listeners, many of whom are students and early career researchers, with one principle for designing in extreme environments, what would it be?
Yeah, so think outside of the box, and don't be limited by your intuition, that come maybe from your from your education and experience or past experience. So they the education and past experience helps, but they sometimes also put limitations that you don't realize. And so it's always when I think, is at least from my experience, when you kind of think, turn around the problem, thinking about, trying to use failure mode, or think about structures that are not so static. They can be flexible and stiff, right? And I think that's typically, that's usually when you have, you'll find amazing things, and there are things you don't expect. So I think that's a little bit of, I guess, what I learned through the experience, through the years.
Kawai, it's been an honor to have you here. Thank you so much for sharing your insights and expertise.
Thank you for the conversation. I very much enjoyed it.
To everyone else listening, this is the Omar Aleli podcast. Thanks for joining us, and keep exploring.